Hey man, what's up? Oh, I'm not. Huh.
Good morning. I'm going to make a few comments about problem set 2 and the solutions, the problem set you've just hopefully completed. That together with problem set 3 will be posted on Moodle this afternoon. And the numbers I use, this is the second posting I've made, so this is 2021.2. And you should be able to find it there. I would encourage you to start problem set 3 today. Okay. You have enough stuff to start it without a doubt. And if you do it a bit earlier, then it'll help you prepare for the test, which is test 1, which is next week on Friday, February the 12th at 8:30 in the morning. That test will be on problem sets 1, 2, and 3, and on the examples done in class. There'll be no derivations. Somebody asked Mohammed about the formula sheets. You make up your own formula sheets, as I've said in the past. You think about what formulas you would need that you wouldn't remember easily, or perhaps not correctly, to do the problems in the problem sets and to do the examples done in class. There's one example, example 4, which is a derivation of 2D elasticity for an axisymmetric problem. No, you're not going to have to do 2D elasticity. The results for that example would be quite general. So essentially, that's a stress concentration factor of 2 all the way around the hole. So that's examinable, but doing something like that, no, you haven't had enough experience to do 2D stress analysis. But everything else is fair game. Are there any questions? Oh, with the necessary charts? Yes. Okay. So what you'll get on this test is material properties. Okay. You won't. Sometimes in the homework, you won't be given the material property. This is the design course leading up to design. More often when you're doing design, you're not given all the information you need. And so as opposed to when you're sophomores, all the problems have all the information you need and you don't have to get anything. You can expect as we go through this class, there'll be some problems where you have to go get stuff. You have to look it up. Okay? That will not be the case on the test. You'll be given all the material properties and any stress concentration factor charts that you need, you'll be given. Okay? You may be given a bunch of them and you may have to pick the right chart, but you will be, the right chart will definitely be included. Any other questions? You know, this, what you'll see from the practice test I put together, the nature of the test, there'll be short answers and long answers, half an hour for each of them. Okay, and these are not trivial. These tests. If you know how to do the homework, you know, understand how to do that well, then you'll be in good shape. If you understanding is limited or weak, then it's going to be a very tough test. Okay, so how do you get understanding? Well, you do the problems and you look over the solutions to make sure you've got them. It doesn't really matter you got them wrong initially. What matters is you know how to do them ultimately. With that in mind, let me give you some comments on problem set 2.
Will we be able to take the exam in person?
If you want to take it in person, please email me at my home address in the next couple of days, okay? If that's what you want to do. If there's enough of you want to do that, we'll try and set that up, okay?
Thank you.
Okay, so for any of you that want to take it in person, email me before the end of the week, and I'll I'll try and find a room if there's enough of you, so you can take it in person. That's probably a good thing to do. When you take it in person, you can discuss with other people after you get out of the exam what you probably should have done. Here's problem set 2. I'm not going to go into these solutions in any great detail. I just want to give you some of the ideas. The first one was problem 4.1. This is problem 4.1 here. And I asked the question, at what sections is P upon A the average stress? Well, P upon A is always the average stress, but sometimes there's no disruption to the stress, and so P upon A, the average is equal to the maximum. So right across here, the stress would be constant. So P would be constant. B would be constant. This is gradually tapering, but it's very gentle taper. So this would be where the stress all the way across is P upon A. If you start going near here, there's going to be a stress concentration. Here, the stresses will be bigger at the outside edge, and they'll be different down here in this corner. They tend to go to 0 in the corner. Okay, so it will not be uniform there. Okay, but here you're applying the load, and so there'll be a peak stress in the middle, and the stress it'll be a lot bigger than P upon A. Okay, by the time you get about 2 diameters down, that stress distribution coming from this concentrated load will spread out. That's like St. Bernard's principle. So every time you use nominal stresses in a component, you want to think, well, what are the disruptions to it? Well, at places like this, this, and this, there really aren't any. And so the nominal stress stuff does when you're doing your design. This problem here, is the solution. You apply a torque. Now,
window is actually perfect for 20 seconds or more. That's what we used to call the 20-20-20 rule. And then I usually would add an extra 20 to that. The fourth 20 would be during those breaks, either close your eyes and be, sort of zoom error. And we can actually close our eyes and not be judged by our superiors, our bosses.
Mute your mic.
Close those eyes, what you're doing there by closing the eyes.
Right. Okay. So the shear stress is linearly distributed, and its maximum value is on the outside 16 T upon pi d cubed. Power, as I gave you, is T times omega, so you can get torque from the power of the omega. The power is given in horsepower. 550 foot-pounds per second is the power, which I think I gave you in the hint. 550 foot-pounds per second is 1 horsepower. Okay, so to convert this to foot-pounds per second, you need to multiply by 550. This was given an RPM. You want to make these radians per second, and so it's 2 pi and 60 seconds. That'll be radians per second. And that gives you the foot-pound force. To use that in one, you've got to make it inch-pound force. In Mechie, we usually give torques in foot-pounds force. Okay. But if you want to use them for stress analysis, you've got to multiply by 12. And when you do that, you get the following. I did this in KSI. It's quite okay to give your answer in PSI. You just have to have a bunch of zeros. Typically, you want to work to 3 figures. Now, you want to have the same stress with a hollow. This formula was like 16 d upon 2 upon j, where j is the polar moment of inertia. And so the d's cancelled here, but this d's will not completely cancel. Well, they will, but it's going to be a little bit different here. This is going to be j, it's going to be d to the 4th, and it's going to be minus 0.85 d. That's a 4, okay? D to the 4, okay? Then the d will cancel, and you want to make these two equal. Then you're going to have, after I divide by the d, you're going to have d cubed 1 minus 0.85 to the 4th equals d cubed, and you solve when you get d is 3.2 inches. And you can compare the cross sections, and you find you get about a 50% saving in weight. So one of the reasons I picked this example is if you can, when you've got shafts, if you can make them hollow, you will save a lot of weight. Okay, so it's a very effective thing to do.
How did you get the d to the fourth minus the 0.85 d to the,
Okay, that's because this formula, you need to go back and look at your strength of material, 16T. That's what it was. But when you get J, when you have J and there's a hollow, then it's going to be pi. So you need to go look that up. Okay, so it's 16 R. Sorry, it's TR upon J is what the formula is for the shear stress at the outside of a shaft. And so if you go look up J, where you get 1 upon 16 d to the fourth when it's solid, but you get a different J when it's hollow, and that's where that comes from. Okay, but you need to go look that up. The reason why this is working is that you have this linear distribution of shear stress. So this part inside is kind of lazy. It's not doing much. And so you remove this, you only have to make this a little bit bigger to replace this load here. Okay. And so it's always efficient. Now, sometimes it's hard to do, so you don't always do it. So. The second problem, like of that nature, this is the book solution. Let me make some comments about the book solution. And a similar thing happens. This is in bending. In bending, you have the same sort of thing. You have a linear distribution. So, so the stuff in the center is kind of lazy. The book answers, when it comes on, use them, they always repeat the problem and they restate the assumption. In reality, you're not going to have time to do this, but it's not a bad idea to have this in the back of your mind. Okay, and these are the assumptions. The material is homogeneous and elastic, and there are no stress raises. Okay, the bar is initially straight. And the analysis is essentially parallels what I did for the torsional thing, and you get a reduction in weight. Now you have to be a little careful that if you make these two things too thin, you'll get buckling. Okay, and the first example, the thickness was still about 1/4 of an inch. A 1/4 of an inch of steel is not going to buckle too easily. We'll talk about buckling later. Number 4, what you've got here is, this is common practice in mechanical engineering. This thing here has a torque around here, and so you have a torsional stress all along here, which is maximum all the way around here, and then pushing down here, it has a bending stress, and so the maximum stress is going to occur here. You're going to have to combine these stresses. The max bending stress, that's at 32 M max upon pi d cubed. M max equal F times this length and plus this length. And tau max is the 16 T upon pi d cubed, it's solid. Okay? And T is F times this distance here. Okay? That gets you the local maximum from that particular source, from bending and from torsion. That's not quite the same thing as the maximum values. The maximum values, you have to combine these. Tau max, there's only one normal stress, divide by 2 and square it, and that's the tau t squared, and take the square root. And to get sigma max, you take the average stress, sigma b max upon 2 plus tau max. And these are just the calculations. And one of the things we're going to do in this course is we will use both standard US units and we'll use SI units. Why do we use both? I think you're going to encounter both. In the traditional industry, like oil and gas industry, predominant units are still US. That's easily called it predominant. ASME is moving towards SI units. If you write papers, they have to be SI units. So you're going to start to see both. We're going to do both. And when you're working with SI, you have a Newton over a meter squared. That's a Pascal. Okay, Newton meter squared is not really a unit. You should call it a Pascal. And more often than not, for the sort of magnitudes you'll be dealing with, you're talking about megapascals or 10 to the 6 pascals. Okay. Strictly speaking, in SI units, you're not supposed to have numbers bigger than 1,000. So if you had, 1,200 pascals, that would be 1.2 kilopascals. If you have 67 million pascals, that would be 67 megapascals. You're really supposed to use the prefixes M for million, K for 1,000. With the standard US units, it's optional whether you use KSI or SI. So problem 5, it's like a problem I did in class, but the thing is here, you can get the force F because this has to be in equilibrium. So the torque applied here has to be equal and opposite the torque applied here. So you can get F, that's no problem. But this thing here, this 4,000 newtons, well, F is going to be 2,000 then because it's got twice the radius. Okay. So but the 4,000 acts in the vertical plane and the F acts in the horizontal plane. So you have to combine these two bending moments. Okay. They're orthogonal. So it's similar to what we did in class. But here's the sigma B max and tau T max. Okay. And then you can combine them just as we did before. And the torsion is straightforward. That torque gives you, sorry, these solutions are going to be, as I said in the beginning of class, are posted, going to be posted this afternoon. So you don't have to write these down. Okay. But if you do the bending moment diagrams, these are orthogonal planes. This is the vertical plane. That's the one with the 4,000. The horizontal plane has the 2,000. It has a smaller bending moment. And these are vectors. Mohammed, did you post the solution to homework 1?
Homework 1.
Did you post the solution?
No, I think I'll post, okay.
Okay, Mohammed will post the solution to homework 1.
Yeah, I'll post it now. Okay.
He should have done it. Okay. All right. And so this is a vector and they're at 90 degrees. So you take their two magnitudes and square them and add them. That's the resultant vector. In this case, it doesn't make much difference. You wouldn't be badly out if you just use this. But the other cases, that'll not be so. So you want to learn how to do this. Okay? So you had, and then you get the following answers. I'll let you look at the details. And the last problem I want to make some comments on is a cylindrical pressure vessel. And the first part of this is straightforward, using the formulas I gave you. Oh, the transverse shear stress, the one due to the shear force is nearly always negligible. So somebody asked about that. It's in books. It's very, very seldom as a matter. And its peak value is at the middle. And that's not where you're getting the maximum shear. The maximum shear in pure bending is sigma B upon 2. And that's on the outside at 45 degrees. Okay. And that's usually much larger than the shear force in the middle, which is something like 3B upon 2A, depending upon your cross section. So that's an academic exercise largely. I've never seen it matter. So this is a simple calculation for this PR bar upon 2. Okay. And then tau max, this is one of these cases, it's a 2D analysis, and then you have to go, you've got these principal stresses. The hoop stress is going to be the biggest. The longitudinal stress would be about half of that. And then in the other plane, you'll have a stress of 0 on the outside of the vessel and minus P on the inside. So if you take the minus P, it'll be sigma 1 minus P, you add the P, and that's where that comes from, and you get this. Okay. Now this is the external pressure, and there's a lesson here. Okay. So here's the problem I want to solve. I've got external pressure. Well, that's equal to put pressure all the way around, then subtract the pressure from the inside. Okay. When you put pressure all the way around, then the stresses, both the stresses, are equal to minus P. We're going to be talking about finite element later in this lecture. We'll use that called a patch test. Doesn't matter what the shape is. If you put it under all-round pressure in 2D, also in 3D, but in 2D, both normal stresses are minus P, and there's no shear stress. It's just all right. So that's the answer for that. This is as before, is PR bar upon 2, just the same as we had on top here. Okay, but we're going to subtract it. So you get minus P minus PR bar up 2. Okay. And so the answer would define the tensile stress. Well, there's no tensile stress here. So the answer is 0. But here's how you find these hoop stresses and the longitudinal stress. What you do is you add P and change the sign. Okay. Let me write that down. Oh, and then the maximum shear, I'll let you think about this, but you don't want to take the minus P off because it'd be a negative compressive stress. Minus P would add a P, and that would make it smaller. You want to take sigma 3 with 0. Okay. And you get the same. You'll get exactly the same. Okay. So here's the rule for external pressure. And that works for both the longitudinal and the hoop stress. Add P, then multiply by minus 1. Now what you may not have thought of that, and that's fair enough. You haven't had a lot of experience with it, but unfortunately the pressure vessel handbook fails to add the P, and so does Roget's formulas for pressure vessels. They're wrong. And it turns out that when you have external pressure, the walls tend to get a bit thicker to avoid buckling, and so this P is not insignificant. So when you want to get external pressure, take your internal pressure formula, add P to it, and multiply by minus 1. And the last problem was fairly straightforward. I'll just let you look at that. Any other questions? Okay. We're going to continue talking about KT, but let me reiterate why it's important. Now, KT is extremely important for repeated loading, and that's what you're going to have to deal with most in mechanical engineering fatigue. Okay. And the book makes light of KT for single loading, and you need to be careful. So the safe rule is to take your failure stress or your stress at load where it breaks to be the ultimate strength divided by KT. Okay. you will get less, you will get a higher stress if the size effect of the extent of the stress razor is comparable to microstructure, but you need to know that. So this is safe, okay? That's what you want to do unless you know otherwise. Now, the size of the stress region, or highly stressed region, will not be, say, the radius of the hole. It'll be a small fraction of the radius of the hole. The size of the microstructure can be much smaller still. When that's the case, you want to use this. Now, very seldom do we load brittle materials with one-shot loading, but you will deal with insulation and ceramics and stuff like that. And sometimes they take a load. When they start to take a load, you want to start off with this when you're designing them. The book makes the argument, if you have a ductile material, the yielding redistributes the stress, so you get to close to the ultimate stress. You won't quite get there because their argument is a little oversimplified. And that's basically okay. You need a little bit of a safety factor there. On the other hand, when you start to yield, that will be reduced by the KT. I showed you the C clamp there. That's a big clamp, okay? It's thick, over an inch thick. It's 12 inches long, more than 12 inches long, and so on. It's a very big piece. It almost certainly yields when you get this, the stress at yield, nominal stress at yield will be SY divided by KT, okay? So, and that can be failure. For those C clamps, that would be failure. So while both the book does say these things are very important for fatigue, they're also not insignificant for single loading. But typically, you don't do brittle materials with single loading. You try to avoid loading brittle material. On the other hand, these C clamps are built for single loading, and this would definitely screw up your design. Any questions on that? We also looked at, I want to look at this some more, so we'll do this. The ellipse. I'll orientate this at 90 degrees to what I did in the past. And if I do this, and if somebody asks in class, then that would mean that the load is orthogonal to A, so it would be loaded horizontally in this case. The one I did earlier was loaded vertically. These are the same configurations, they're just rotated through 90 degrees. So you're going to get maximum stresses here, and you're going to get minimum stresses and compression here. for these sort of hole problems, the stress concentration factor or the increase of stress, you always have a 1 here because you've got rid of the hole completely. And so if you made A go to 0, you still get sigma naught. So you expect to have a 1. And this is the part that enhances the stress. And you can write this in terms of the local root radius. So R is the tip radius. If B equals A, then R is the radius of the circle. If you make B go to 0, that would make R go to 0. And this thing becomes a mathematically sharp crack. It actually has no dimension this way, so the 2 lines in some sense are an exaggeration by me, just to try and make it clear. And what this formula tells you is that has a very big KT. Okay? In fact, if you make R0 or B0, sigma max tends to infinity. That is quantitatively correct. There is a large stress there. Sorry, quantitatively incorrect, but qualitatively, I got this backwards. It's correct. Okay. You can't have an infinite stress, and no material could take that, but you will get a large stress. And I think I sort of demonstrated this to you in the first class. There is a definite stress concentrator of the crack. Here's a piece of paper, and I'm going to pull it on the bottom part here, and it's wrong. So I pull it, same piece of paper. Now it's got a crack coming down, just meeting the top edge. Then right. So there is no question there's a high stress there, but it's not infinite. Okay, it did take a load. Well, what's happening here? Cracks are important in mechanical engineering. We try to design parts so they can even sustain, they can even exist with a crack, okay, without breaking. Okay, so we don't want them to fall apart immediately, and so we're going to be concerned about cracks, and we'll deal with that a bit more. But what's going on here? Why do we get this infinite stress? Well, it's the same thing as I asked you about when the hole closed. When the hole closed and you had it under, say, tension, you still got a stress concentration factor of 3. Well, when the hole gets very small, then you have the atoms on either side of the hole start to see each other. They have the same law that they have in the bulk of the material. In the bulk of the material, these atoms are connected to each other. When they start getting very close, they start to see each other again. Okay? And so the stress-free boundary conditions that are used in the elliptical hole problem start to stop applying. So where this mistake came from, or this non-physical result, is the 2 sides of the crack will see each other. And that'll get rid of the singularities. This is done in detail, and this is not examinable, but when you get out, you might want to look at this. And this is explained in this article. And what you find then as a result, that KT does still equal until you get to very small radii. This is true if the radius is greater than 0.04 microinches, or even simpler, 1 nanometer. So you can use this formula. So if you've got something with a small radii and you go measure it, you're going to get something bigger than this. This sort of formula will work. You get very large stresses. The good news is that they operate over very small regions, and sometimes you get strength size effects that help you out. We can also use this for extrapolation on your charts when you have small radii. Let me show you. This is going to apply for pretty much any radii you look. Actually, what happens when you get inside this radii, the stress concentration starts going down and eventually goes down completely, and the crack is closer. But you can use that formula to estimate KT for small r. What you've got is delta KT. I'm going to find that as KT minus 1. You've always got the 1. Then that's proportional to the inverse square root of a dimensionless radius. Let me do an example and show you how this works. This is going to be for a fillet. I'll give you the figure in just a second. So that's the problem. Here's the appropriate graph from the book. We're going to say R upon H is 0.05. H upon H is 1.2, that's this line. And so we get this value here, which I've estimated is 2.01. Then we're going to try and estimate the value when you get to 0.12. We actually have it on the graph. So we'll be able to see how well this estimation does. We're going to pretend we don't have it, and we're going to estimate it. So we're going to try and estimate this value here. I said delta KT was proportional, inversely proportional to the square root of the radius, and that this is a dimensionless radius on this graph. It's R upon H, where H is the height of the section. So what that means then is that delta KT for R bar equals 0. This is proportional to the square root of 0.05, because it's inverse. This is proportional to the square root of 0.012. Okay. So that if we compute that, 0.05, 0.12, square root of a little bit over 4, that's 2.04. So delta KT for R bar is this times this. What was delta KT for 0.05? Well, it was 2.01. You subtract 1, it's 1.01. So that's 2.06. So then KT, you add 1, you get 3.06. The decimal place, if you take with a grain of salt, it's just an estimate. If we go back and look at the figure, how did we do? Well, this is the answer. It looks like about 2.81. So this extrapolation method is a little bit conservative, okay, but it's reasonably accurate. But it's reasonable. Okay? It's much better than linear interpolating. Suppose you took this value here and this value here and drew a linear line, you'd be way low. You'd be about 2.2, okay? So this is much closer than that. And you'd be non-conservative. So when you've got charts and they stop at some radius and you want a smaller radius, you can use this approach to try and estimate the values for smaller R. Are there any questions on that?
Yes.
Yep.
Do those red lines max out at the 2.8 or do they keep going and they're
Oh.
just cut off?
That's all that's on this chart, and that's going to happen to you all the time. The chart will stop. The answer is the people who assembled the charts, that's the values they had. Are there any other values somewhere around? There might be, okay? And we're going to start talking about finite elements. And one way you could do this accurately would be to do your own finite element analysis if you had the small radii. Okay? But what you're going to find is that this approximation, this 1 upon the delta KT being proportional to 1 upon the square root of R bar, works better and better the smaller the radii are. It doesn't work so well if I was to do it back here and try and get this value from this value. Okay? But once you start getting smaller, it works pretty well. But yes, whoever put this chart together, this is the values they had. And from your point of view, your charts are going to be what's in the book, okay? When you get out, you'll probably want to use Peterson, which I gave you the reference for. It's got far more charts there, okay? Well, let me start talking about what you're going to do in practice to get these things. And that is, you're going to do finite element analysis. So the first thing before you start doing any finite element analysis, you want to make sure you need to do it. To do it properly is quite a bit of effort involved. To get an answer from finite element code after you've had some training in how to run the code is not so hard. To get the right answer is not so trivial as we'll talk about today. So you definitely want to go and see what's available. And the most extensive set of stress concentration factors is that book by Pilkey and Pilkey, Peterson Stress Concentration Factors, 3rd edition, I gave you a reference to. So you go check in there, and you may find something that's similar, okay? But there's going to be problems that don't. that don't. And I went and looked. There are 53 figures in Peterson for U notches, but there's none that has the loading like the C clamp. Remind you, here's the C clamp. Now you can get this sort of shape, but you won't get it with this load here. And with some skill, you could get an estimate out of it, but it's not going to be easy and it's not going to be that accurate. Okay? And so this is the sort of thing you want to do. And these guys want to know what's the big stress here. So when is this thing going to be okay? How big a force can I take without it yielding? When it yields, it stops clamping things. And so they want to know that. So that's why we did the C clamp. We couldn't get them an answer from Peterson. How are you going to do this? Well, there are a series of standard codes that have been carefully verified, the codes themselves. The oldest standing one of these is Nastran. And quite possibly the one you'll use most is the one that underlies SolidWorks. I know John Swanson wrote this a number of years ago for Westinghouse. It's a carefully verified code. I consult with these people. I know some people now because it's a good company. I haven't actually worked with Nastran. SolidWorks, there's a professor at USC wrote the finite element code, and I think it's a pretty good code. So all of these codes work. There may be some other code. I'm confident for your stress analysis, for the sort of things we're going to be talking about, that these things work. Okay. When you get out in practice, you may want to read a little bit more about the underlying concepts to understand it better. But you don't need it, okay, to run these codes. You don't need to do this. But when you do, I've taught the finite element now for probably 20 some odd years. As a result, people keep sending me books. The best book I've found is the following. I have the 4th edition. I don't think they've written any later edition. But you might find some other book that you find very readable. You don't really need to read these books to understand and be able to use these codes. Okay? It's useful, but you don't have to. You don't have to have a course in finite element algebra, and you're quite possibly not going to get one. The key is going to be, how do you know you got the right answer? And that's called verification. Okay? Codes themselves. Well, these codes that I listed for the standards of analysis that we're going to talk about have all been verified. You don't have to worry about that. They were probably verified about 30 years ago. Okay. There are some more tricky problems where there's perhaps some questions that the people who develop these codes spend quite a lot of time testing them. Okay. Nastran was the finite element code underlying the moonshot, and that was tested a long time ago. I imagine it was verified in the mid-60s. But a key for you is input the code. This is tremendous scope for screwing this up, I'm sorry to tell you, okay? And so some of the documentation has improved in these codes, and so that makes it less likely. It used to be, we used to say in answers that unless you'd run that particular element, you wouldn't know how to do it from reading their documentation. You had to get with somebody who had run it in order to do it. But I think their documentation's improved. It's still got some ambiguities, so it's not that hard for you to do one thing when they meant you to do something else. It's very easy to make mistakes, okay? The other thing, so this we're going to deal with, okay? With practice, you can get this down. The first few times you use codes, expect to be challenged by this. Okay? And these things all involve approximation. There's an underlying approximation which occurs within elements. And when you make an approximate, it'll differ from the actual function. And as you refine your mesh, hopefully that goes away. We have to spend some considerable time talking about how to do that. But here's sort of what I mean by discretization here. Suppose I have a function that looks like this. Then if I approximate it with one constant, I would take the middle value. In which case, this would be the error here, this would be the error here. Okay? If I approximate it with two constants, then things are starting to get a little better.
Can you push the paper up, please?
Oh, sure. Sorry, my mistake. Thank you. So this error has gone down. Still the biggest error is back in here, and it's going down out here. And I start doing four constants. You can see that the error keeps going down. Okay. So as this discretization or approximation error will reduce as you refine your mesh. And that's what we're going to discuss and figure out how to do it. But this sort of constant approximation is the one used for stresses with 4-node quadrilateral elements. Okay, so as the stress varies, you have constants, but as you make the size of the elements these lengths get smaller and smaller, you'll get it more and more accurately.
So, Dr. Sinclair,
Yes,
will we be using the likes of SolidWorks for this course?
probably not. We probably don't have time. But I think when you get to capstone design, about half of the groups use finite element analysis. Okay, there is a finite element tech elective, and it's a good idea to have one member of your group at least take that. It's a good skill to have when you get out. I think you're going to be more marketable because people are using more and more finite element. There's a generation of engineers, my generation, are very suspicious of it. I think it's a fantastic tool that's used properly. They're very suspicious of it because people get really seriously wrong answers. But it's really valued when people start getting right answers. So right now, we don't have anything that requires you to run the finite element code. We in the capstone design, we used to have, I used to give some lectures on how to do it, and we'd have an exercise there, which everybody did. I'm not sure if they still do that or not. And there is a tech elective on finite element analysis you might well want to take. Okay. You can learn this stuff by yourself. That's more or less how my first finite element analysis, more or less what I did. That was about 1970. But it's easier with a course on how to use these codes. Let me just finish with a couple of things about checks. So how do you beat these problems? Well, this thing here, you want to do test problems. You don't want to just start off doing the problem that you wanted to do. You've got this configuration, and you went and looked at Peterson, and you said, well, I can make a rough estimate from Peterson, but it's not very good. I'm going to analyze it. Then you want to analyze something. So you want to take something from Peterson that's similar and see if you can do it. Hopefully with the same mesh, okay? And so as I said, with the C-clamp, I found for different loading, I found a problem in Peterson, and we could set the mesh up, same mesh we're going to use. I'm going to talk about this a bit more, and then run that and see if we've got at least similar answers. There are the answers in Peterson are not 100% accurate. A number of them are done with strain gauges or with photoelasticity, and then there's experimental error, and so the errors can be as high as about 10%. But that means, though, that you want to get within 10% of the answer. You can also do a thing called a patch test. Now, this is a bit like what I talked about for the problem set 2. Suppose you had this configuration. This is a bit like my C-clamp. Well, if you put this under pressure everywhere, uniform pressure all the way around, you have to hold it somewhere to stop it moving. And over here, you have to stop it rotating. So if at one point I tell it ux and uy equals 0, that stops it moving this way and this way. It could rotate. So I come out here and tell it not to move in that direction. That'll stop it rotating. You put it under all-around pressure, then the exact answer. And this works for any problem you're doing. So one of the things you can do, and this is a very easy boundary condition to put in any of these codes, constant pressure. And so you can run it and make sure your mesh is properly connected. If you generated a mesh here and you've connected it to some other mesh and you've got a gap, you won't get constant, okay? And so in simple problems, this is a very simple test. More complicated problems with mixed meshes, this is a good test to do. And it's not a bad check that you can input things. So this is the simplest possible problem you can do, and make sure you're talking to the code in a way that it understands. And mistakes of miscommunication of the code are not all the user's fault, okay? It's a good 50-50, I'd say, between how it's been described, what you say, and your interpretation of it. Okay, so, but at the end of the day, you have to know how to talk to the code. And so this is one test. And these are what you want to do in practice. You want to do a similar problem. I would start off doing the patch test. I would do that first, make sure you can pass that, and then do a similar problem. Okay. All right, we're going to take a break for 5 minutes, and I'll tell you how to beat this discretization error. Okay. Let's take a break for 5 minutes.
Yeah, Dr. Sinclair.
Yes, sir.
Do y'all have any plans on like maybe getting a better camera? Because some of the stuff is still pretty blurry.
I'll talk to Mason and see what we can do. I think, so, yeah, I'll try to print bigger to make it clearer. I am printing a bit bigger. You know, of course, it could be in your reception, but I'll talk to Mason and see what we can do about that.
Okay, because I'm sure there's some classrooms that aren't being used that still have their projectors or cameras that maybe y'all could borrow.
Okay, well, let me see what we can do about that.
Okay,
Another
thank you.
option could be you could upload your note. I guess we can check ours
No,
against
I don't
it.
do that.
Okay.
I don't do that when I teach in class. Okay, so if you want the notes, you come and make them. Okay. But though I think Mohammed is posting video, posting these lectures. Okay, well, let's go back to this. Verifying finite element. Okay. And this is a fantastic tool. You can practically analyze any problem you encounter and get the stresses. Potentially it's great. We're going to concentrate on controlling its discretization error. Okay. But as I said, it's every bit as important that you've given the code the right input. Even after you get the right input, with some experience and some practice, you'll get that. Okay. Some of those experiences can be a little harrowing, but yes, you'll get there. I would say for people who run these verified codes, the codes themselves will be verified and are running it correctly. In my experience, about 30% of the answers are really accurate, 40% are marginal, and 30% are rubbish. So how do you avoid being in that last group? Okay. Well, you have to do these convergence checks. And so converged stresses would imply that further if you refer them, does not change so if they completely converge, they wouldn't change at all. Well, as a matter of fact, they're always going to change. It really should be, this unchanged should be
Dr. Sinclair, could you read that first arrow real quick? It's kind of hard to read.
oh, sorry. Further mesh refinement leaves key stresses unchanged. Okay, we're going to talk about how to refine your mesh, and that will reduce your error. Okay, and so you've converged if you keep on refining, and then nothing's happening to your key stresses. There's no further no further refinement. Okay, that's a hard. Yes. Maybe I have to print bigger still. Okay, I'll try that. Well, that's seldom going to happen. It leaves key stresses with acceptable variations. So they're going to vary a bit. And the particular because we're going to be talking about stress concentration factors, we're going to want this to hold for sigma max. What's going to tend to happen is away from the peak stress, the stresses will converge pretty well, but at the peak stress, they won't converge as well. And so if you have this is some sort of hole here, and then the peak stress looks like this and reduces as you go out. And as you refine the mesh, so what happens is away from the stress concentrator, it starts to converge, and but here it's still changing a little bit. My figure's not that clear, but these values are still increasing. They're increasing by reducing amounts, which is encouraging, but they're still changing. Whereas when you get away from it, initially you perhaps didn't have it right here, but you pretty quickly get it. So you're going to want to get this to happen for sigma max. Okay. So we have to decide how we're going to refine our mesh. Well, there are a couple of things done in practice.
Dr. Sinclair. Is this similar to CFD, where as you refine your mesh, you get more accurate results?
Yeah. Mohammed, this thing looks like out of focus now. That's not focusing properly. Where's the focus?
Can you go to the video on the right side?
Yeah, let's say stop video.
No, just on the. Can you check? Video settings.
Okay.
Oh, wait, it's 8. So it's already. It's okay. Maybe, did you move the,
I don't think so.
Yeah.
Oh, okay, maybe you bumped that. All right. Okay, good. Sorry. Yes, if you do CFD, you refine your mesh in CFD. Okay. CFD typically doesn't use FEA. Okay. CFD, you have time dependence. You could use FEA for steady flows, but if it's computational fluid dynamics, you really got dynamics in it, you have to have uh, finite differences to handle the time value. But there are some CFD codes that use finite elements for the spatial stuff. Typically, they still use finite differences. So, but you have similar concerns. You have to have mesh refinement, which shows that you converge, and you can refine your mesh in finite difference too. There are two schemes that are practiced for mesh refinement with finite element analysis. This is a sequence of meshes with n elements. And the first mesh might say you have 100,000 elements. There's be 200,000, 300,000, 400,000, and you see if your answers are converging. There's a second scheme. HM is representative element size and mesh M. But let me show you how the second one works. So there's my first element, and then I'm going to halve it. And I went to M equals 3. Well, you can see what's happening here. The element numbers are going up by a significant factor. This is 1, it went to 4, it went to 16. So the sequence here so if you started with 100,000 elements, then the drawback of this, that's 100,000, that's 400,000, this is 1.6 million. So you have a lot more elements you're using. Now, of course, one way of beating that would be not to start with 100,000, okay? And then you could keep the number of elements down, and we'll come back to that if we're going to use that. Okay? There's a little bit of a tendency by finite element users to start with a mesh they think is going to do the job, then refine it. And if they start with a mesh that has literally thousands of elements in it, then these sort of mesh sequences start to become difficult. Even this can. So you really want to start with a relatively coarse mesh when you're doing this. Let me show you which of these works and why. So we can do a check. I hope. Okay. It may be that in math classes, they no longer teach series, but we can use series to sort of see what sort of convergence check work. By series, I mean Sn is a sum to n terms of some computed quantity. And then 1 here, this is just 1D, would have n, 2n, 3n, and so on. But 2, this here, you'd be halving a mesh size, but it's only 1D problem, so it would go n, 2n, 4n. Okay. On the particular series I'm going to take an equals 1 upon n. You may have met this, it's called a harmonic progression. It's the sum of the reciprocals of the natural numbers. Here's what happens when you do it. Or just 1, it's 1. 1 plus a half is 1.5, and so on, 1.83, 2.08. And if you keep on doing it, 7, you get 2.59 and 2.72. So we could take the differences and see what's happening to them. And we'll use it for 1. Well, here are the differences. Between there, 0.50. Between there and there, 0.33. So we're checking how much it's changing with this sequence. Okay. And it's going down. That looks promising. In fact, it's even gone down further from 0.13 here. So it would imply it's converging. If, on the other hand, we did it with scheme 2, then between 1 and 2, we get 0.5, just as before. Between there and here, we get 0.58. Between here and here, we get 0.64. So the first sort of sequence of meshes in 1D sequence of sums would imply that these numbers are going down and the series are converging. The second one says, well, they're increasing, and so it's diverging. Well, what's the answer? Well, this series diverges. The series diverges. You can estimate this series. Here's its values, and you can take, it's about 4.5. You can estimate the area under this thing with an integral. And so a reasonable estimate for Sn of this function, which looks like 1 upon x, integrate 1 upon x, you get log x. You put the upper and lower limits in, and you could check this approximate. That's what I'm doing it, I'm adding it up using this approximate formula. This should be n plus a half. Sorry. My mistake. So it's accurate. So this means you may have had that in the math class already. So this series does diverge. So you don't want a convergence check that concludes it's converging when in fact it's diverging. So that means that this sort of scheme does not work. I still see it practiced with finite element engineers, and part of their reason is, well, it's too expensive to do the other one. Well, not if you start with a coarse enough mesh. Okay, that's what you got to do. So this is what we're going to do for convergence check. We're going to have average element extents. These element lengths may vary throughout the mesh. Okay. And what this is going to mean is
In that equation that you just wrote, and is that supposed to be nm equals 4 nm minus 1?
yes, thank you. Thank you very much. Appreciate it. Okay. Yes, thank you. So the mesh numbers are going to go up by a factor of 4, which I showed with a little sketch. And actually in 3D, the more and more finite elements being run in 3D, okay, because SolidWorks is a great 3D geometric packaging modeling program, fantastic. And then you can ship it and do finite elements straight from that. And so that's easy to do. And so lots of people are doing 3D, even if the problem is predominantly 2D. In that case, the number of elements needs goes up by a factor of 8. So you need to start. Your first mesh better not have too many elements, or you're going to run out of room. Computational facilities are getting so good nowadays that even if you start with a few thousand, you multiply by 8 a few times, you can live with a few million elements. But one of the things that happens in practice is people go and build their first finite element mesh as if it's the right mesh to do the problem. No, what you want to learn to do is to build the first finite element mesh that might give you a halfway decent answer. And then you can refine it and see by the time you get to the mesh that you think's good, whether they're converging or not. But the other system does not work. And moreover, I've seen it give results where it says things are converging and there's a stress singularity that's not converging. But once we've got it converged, we need to estimate the error. And things are starting to converge. We'll start off imagining we know what the error is and we know the exact solution. And let's think about how that works. And then we'll try and get some estimates. So let's imagine temporarily that we had the exact value of what we're trying to find. Okay? Obviously, if we did, we wouldn't be doing the finite element analysis. So this is an imaginative step. But if that's the case, if we, or perhaps you can say, God is looking down and she knows what it is and she's going to glow on it to us for a wee while. Okay, so then if you subtract your value of, and typically it'll be less, but it wouldn't matter if this what sign this has. If you subtract the value from mesh M, then that'll be the error in mesh M. And these things converge with finite element according to a convergence rate. And you can show this with a piece of mathematical numerical analysis. This is this EM, E naught is the error when the mesh size is H naught. So if you put HM equal to H naught, this would cancel, and this EM would be equal to naught. And CM is called the convergence rate. If you've had some numerical analysis, you'll be aware that there's always convergence rates of certain approximations. It turns out for a finite element, we have 4-node quadrilateral elements, then your approximation function the stress is essentially as a constant. It's got one linear term, but it doesn't have the complete terms. So it's missing linear terms. So the parts that are missing gives you the dominant error, and they're linear. And so you tend to converge linearly. What does that mean? It means you halve your mesh size, you halve your errors. Okay? We're going to approximate these elements with 4Q. On the other hand, if you have CM will tend to 2 for 8 nodes, which we'll call 8Q. Okay. With 8 nodes, around each node introduces a degree of freedom in your approximation, and you can get a linear approximation for your stresses. And then the thing you're missing are quadratic terms, and so this is the term missing from your approximation. That's what the errors dominantly behave like. With quadratic convergence, CM equals 2, then if you halve your mesh size, your error goes down by a factor of 4. You could question, therefore, why don't you always use this? Well, these have more degrees of freedom, so they're more expensive to use. So these are the two dominant elements used in practice. These are slightly more robust, but they're both used in practice. Well, let's try and relate this true error to delta sigma m. Because we can get delta sigma m. What is delta sigma m? It's the change in the stress as you refine your mesh using the sequence where you halve element sizes. So it's just that change. We could write this.
What does that top sentence say? True error
And.
And?
Yes, okay. It was supposed to be that simple. Okay. Sigma m minus sigma e minus and I've really done nothing here. This is minus sigma e minus sigma e, the two cancel. But this is sigma e minus sigma m was em. Okay, so this is minus em. This is minus would make that plus sigma e minus sigma m minus 1. That's going to be plus em minus 1. So delta sigma m looks like this. We'd like to get rid of em minus 1. We can use this convergence ratio over here. So I just put HM minus 1 for HM, and you get EM minus 1. Okay. If that's the case, then I can get the quotient. Well, the E naught and the H naught is going to cancel. And so you're just going to get H. But this is twice as big as this. So now I can substitute EM minus 1. EM minus 1 is EM times 2 to the CM. So I would have EM into 2 to the CM minus 1. If I divide through, then EM so this tells us how this exact error is related to the change in the stress. It's 2 to the CM minus 1 when we're when we're halving element sizes. Okay. The only problem with using this for an estimate is we don't know what this guy is. We can get this guy, but we don't know what that guy is. If we can get that, we'll get an error estimate. Let's do that next. Well, we could go get EM minus 1 using the same formula. And it would be CM minus 1 because that will not necessarily be the same. But I'm going to assume that this stays reasonably constant. We'll find out that it varies a little bit, but it doesn't vary that much. So we're going to say that CM is approximately the same as CM minus 1. Then I can divide these two together to get the quotient. I already had that EM minus 1 over EM is 2 to the CM. But what's it going to be? If I divide this by this, I'll just get delta. Sorry, that should be my mistake. That should be sigma m minus 1. Sorry, the previous, my mistake. So this 2 to the CM is just the ratio of the, under this assumption, which is approximately true. It's just the ratio of the stress increments. So now we have an estimate. I replace this by this. And I can turn this into percentage error. In fact, we'll use epsilon for that. And it's going to be an estimate. So this is an estimate of the absolute percentage error. As of right now, this is not in final element books, which is why I'm giving to you, so the derivation. But in terms of what, you're just going to have to use this. Let me tell you how you use this. So here's a summary of what you're going to do. There's a derivation like this in one book on verification by Roche. This is what you need to practice. Use that mesh refinement scheme in 2D. Then we're going to check that it's converging. it's going to turn out when you do some finite element, occasionally these things change sign. And when that happens, it's called non-monotonic convergence, and it's very difficult to estimate the errors reliably. What's also going to happen is if you have a big enough stress concentration, the stress increments initially will be increasing as it tries to get up to this big stress. And then when you get closer, it will start to decrease. So we're going to wait until it starts to decrease before we estimate the error. So if this holds, only when this holds, then we estimate the error with this formula. So let me give you an example and show you how this works. Some similar things are done in CFD. Okay, so not quite the same, but very similar. This is this peak stress here. There's a sequence of meshes. Here's the original first mesh. Okay, it's refined near the area where the peak stress is. It's actually very structured here. So the elements here are being literally halved. Okay, but there's some transition meshes where they've been halved on average. And here are the results. The angle varies, but these values of Km are dimensionless stress. Okay, and so I'm just going to write these down. These were done with 4-node quadrilaterals. So here are the values. First of all, we can check the mesh refinement. So we didn't start with a mesh that was 100,000 elements. Okay. Still, that first mesh I showed you is quite a good mesh. Then it goes up by a factor of 4. Not quite, but certainly to 2 decimal places. And then another factor of 4. And finally, we get to about 100,000 elements in mesh 4. You can keep going with current codes. You can get to the million. So that's okay. Here are the stresses. Now, normally we're only interested in 3 figures, but to do these stress estimates, area estimates, we have to take differences. And you want to get the differences, these delta sigma, to three figures. So we're going to have 4 decimal places here. So sigma m we got, and this this was under Km there, but it's sigma max divided by sigma by sigma norm is what it is. Here are the values. It's changing, and here are the changes from this minus this. This from this. And this from this. So what we have here is that these stress increments, they're all increasing, so they're same sign. So we do have they're all positive here. They could be all negative. We also have that they're uniformly decreasing. And until we pass these convergence checks, we don't try to estimate the errors. But since we did, we can now estimate the error. We use this formula here. So we can get an estimate from mesh 3. We usually put a hat on it because later on we're going to have some exact answers for this from some test problems. And the hat means it's an estimate. Then it would be delta sigma 3 the absolute value is the same as the value because it's positive, times 100 over the value, the current value, times the ratio of these two. This is delta sigma m minus 1 over delta sigma m. This is almost double this, not quite. So this number is a bit less than 1. This would be 2.6 divided by 2.4. That's about 1. This number is a little less 1. So we get something that's slightly bigger. And since this is an estimate, we would only report it to 2 significant figures. It is just an estimate. You can calculate it to 3, but it really is just an estimate. And then if we do epsilon 4, then now this number changes to 0.0128. And the current value, 2.4296. Then this quotient, uh, 128 times 2, 254. This number is a little bit bigger than 1, not much, but this number is close to 1. And so we're going to, and this number is about half of that. We get 0.50%. So from this analysis, what we would say then is that KT, which is sigma m, we'd say 2.43. We're not interested in, we have the more decimal places here for taking the differences, and we got 3 figures in the differences, which is good. That's what we want. Okay, but obviously, at the end of the day, we're in 3.43. We'd say with 0.5% error. And in finite element analysis, that's a good result. I'll discuss that more next time, but what levels we need to get to. Now, this is a little bit of a handful when you first see this. Okay. And the reason for repeating is you're not going to find it in the finite element books yet. It will be there. And I think ANSYS, I gave a seminar on ANSYS in fall of last year. ANSYS is moving towards adopting this and making it part of their system, and maybe Abacus will too. Okay. So in which case you won't need to follow this. In the short term, though, for the next few years, you need to have this estimate. I'm going to summarize this thing again when we start off again. You need to have these rules and apply them yourself. They're not going to be applied for you. We can also get an estimate of the convergence rate here, which is interesting to see how it compares with what's called the asymptotic rates. But this is the key thing here. And in order to do this, you have to have this mesh refinement. And if you think about this, if you think about people who started using n plus 2n and 2n and 3n, 4n, what happens if you get to mesh 100n? So the next mesh is 101n. That's a 1% change in your mesh. That's not checking for convergence with the dial. So that scheme was computationally convenient for the people who practiced it, but basically seriously flawed and useless. Now, if you got to 100 meshes and you were quadrupling them, you better have started with a pretty small mesh. You won't be able to run it. That's true. So the other system has a penalty in terms of computation, but it's reliable. It works pretty well. These area estimates do work pretty well. And we'll verify that these sort of estimates work next time. Are there any questions?
Are these formulas that we should make sure are on our formula sheet for a test, or is this more?
Well, yes, you're going to have in problem set 3, which will be posted today, we'll have you doing some of these area estimates, okay? And then I'll reinforce that on Monday. And so unless you remember a formula like that, you'd need to have it on your formula sheet, okay?
Okay. Now, is this a particular chapter in our textbook, or is this
No,
just kind of an extra thing that we're adding?
This stuff is critical for doing finite element properly, but it's not basically in any book, okay?
Okay.
Okay, that's
Perfect.
one of the
Thank
reasons
you.
why I did it, okay? And this stuff was done by ASME Standards Committee on Verification and Validation and Computational Solid Mechanics, and they produced a standard in 2008, I think. And then about 2011, they did an example. And then some of the stuff here is stuff that my colleagues and I have developed. And it's published in, I'll give you a reference, Journal of Verification, Validation, and Uncertainty Quantification, ASME Journal. ASME has realized, starting in 2016, that verification is utterly critical in using numerical methods. And CFD, because they got tremendous scatter when they had round robins, they'd all try and do the same problem, they'd all come back with wildly different answers. They had a greater appreciation for the need to do this than perhaps in finite element stress analysis. And to some extent, people doing finite element stress analysis are a little overconfident. They really oftentimes were getting rubbish. I'll show you some of that later. So no, you won't be able to find this readily. I can give you a paper. I'll give you a reference where you can find it, but that's a journal paper. This approach that we've got for stress analysis is actually in Patrick Roche's book on verification and validation. So that's the only book it's in, and it's in there fairly briefly. So, but you could get it out of that book. No, it would take some digging, but you could get it out of the book. So occasionally when you give a lecture, you're not following a book because stuff's not in the book. Nonetheless, I wouldn't do this unless I thought this wasn't critical. A very good chance that I would say about 50% of you are likely to end up doing finite element analysis when you get out. That might be a little high, but that wouldn't surprise me. In which case, you want to get the right answers. And the way to do that is convergence checks and then check your error. And when your stress increments are the same sign and decreasing, and when they're small enough, then you'll get acceptable errors. And 0.5%, that's a good answer. Okay, that's almost certainly 3 figures here, and certainly 2. And 2 figures is not bad in stress analysis. Okay, not bad at all. Strengths vary by at least plus or minus 10%, sometimes more. And so then your stresses are pretty good compared to your strengths. Any other questions?
By 4 nodes, are you referring to like a tetrahedron?
No. This is 2D.
So we're just, okay, so it's
in a plane, and so
right. Okay.
okay. Yes.
Yeah.
Sorry. So what happens is you have a 4 on each of these corners. You have a node. So those are 4Q. There's 4 of them right there. Okay. So this would be a 4Q. If you start to put nodes in the mid side as well, then you get 8, and that's good 8Q.
Gotcha. I was just trying to see if you were distinguishing between 2D and 3D, but
Yeah,
okay.
this is all 2D. This,
Okay.
This clamp analysis, this clamp plate analysis, it's a thick plate, but it is a plate. So this is a 2D analysis. Okay.
Also, would you mind going back to the series check? I have a quick question
Okay.
about how it converged.
So
The one right before this. So are both of these sheets, honestly? Yeah, that one and that one right there. So for the second one, when we're going by like 1, 2, 4, 8, when you say converge, like this one seems to be growing in value for the 2.
yes,
It seems to be growing in value. So how would you say that that's converging?
I didn't. I said it's diverging. Okay.
Okay.
And this series does diverge. The sum for the series is infinite.
So then why are we using that as our method of increasing our elements if it's diverging?
No, you want, okay, good. You want it to tell you if it's diverging. Okay.
Say that again?
So if you do this test where you do 1, 2, 3, it looks like it's converging. That is wrong. The series is not converging. Okay. You want your series, your convergence check to tell you it's diverging, and these things are increasing. They're telling you it's diverging, and that's the correct answer. This series diverges.
Okay, so you want it to match up with your
what?
analyticals.
Okay. And you will have stresses that diverge. They're called stress singularities. And you want your convergence check to say, you're not getting this stress. In fact, you'll never get it. Okay. And you'd like to learn that as fast as possible, so you stop computing it. You know, when you have a stress that goes to infinity, first of all, as I said earlier on, quantitatively, that number is useless. Secondly, it would take you a long time to compute infinity. Thirdly, if you suppose you ever did compute infinity, what the heck would you do with it? So you want a series, a convergence check that starts telling you not only is it converging, but when it's diverging. Okay. And this sort of check is misleading. It says it's converging. So these are good questions. Thank you. It says it's converging, and it isn't converging. Okay. This estimate is pretty darn accurate. Log of n plus a half. Log of n, and n goes to infinity, is infinity. Log of infinity is infinity. It goes off to infinity slowly, but it goes to infinity. And this is a very accurate estimate. Okay. And so for any finite n, this thing will work extremely well. Probably give you 3 figures. But it says you take n to infinity, this series of 1 upon the reciprocals adds up to infinity. And so this series, this convergence check here was saying, look, it's decreasing. So at least you wouldn't conclude it's converging. Okay. You could even decide, well, these are consistent with diverging. I think the series is diverging without having this estimate. And we'll talk a little bit about that with stresses when this starts to happen. Okay. Sometimes it turns around and goes back down. Sometimes it doesn't. When it keeps on increasing with this check, that means because you've got a stress singularity and you're trying to compute infinity and you want to stop doing that. This sort of convergence check, though, would tell you everything's fine. Okay. It would start telling you that you've got an answer there, which you don't have. So I said 30% finite element analysis in practice is complete rubbish. Well, most of that complete rubbish is people computing stresses at stress singularities, which is a waste of time. Okay. And so this sort of convergence check, I've never seen it start to tell you that the stresses are converging. Well, let me be careful there. I'll come back to that a little bit.
Thank you.
We've never accepted a stress at a stress singularity. Never. Okay. Now, part of it is because in my group we tend to know what the stress singularities are, but even if we didn't, we didn't know what the stress singularities were, then these checks would stop you reporting an acceptable stress at those locations. Whereas if you just do this n to n, and the reason people did this is because they started with a big mix. And then they quickly realize, well, I don't want to, 100,000, 200,000. Pretty soon I'm going to be up to 1 million. That's about my limit of my capability. That's no longer true. Probably you can run 10 million elements now. But even so, you get to 10 million far more slowly when you start with a few 100,000 just going up. And so the reason for doing it was because it's easy to do without thinking about it. Well, it doesn't work. It gives you the wrong information. Whereas when you multiply by a factor of 4 or a factor of 8 in 3D, you are really changing your mesh a lot. If it starts to say the answer is not changing, it is converging because you're changing that mesh a lot.
Right. Okay, that makes more sense. So basically, the more you change the mesh each time, and if your stresses aren't changing because of that, that means that you have an accurate model.
It really is converging. That's right.
Yes. Okay.
And the
All right.
other system, okay, we sounded nice in the beginning because it looked like it was easy, okay, but eventually you're not changing your mesh by much. Okay, when you get to 9n and 10n, you're only 10%. Okay, well, maybe your answer only changed by 10%. You think, well, that's good enough. I'll stop. Whereas we go from mesh 9 to mesh 10. In 2D, there'd be 4 times as many elements, and in 3D, there'd be 8 times. And so when we're not changing the mesh by a small amount, we're changing it by a lot. And then if the answer doesn't change, okay, this is pretty much the answer. Okay.
Yep. Okay.
So
All right.
there are some problems in problem set 3 like this, okay, which I'll post this afternoon. And there'll be, there's a couple of problems like this where you can estimate. And I'll recap this next Monday and talk some more about it. There's quite a bit to handle when the first time you see this. And unfortunately, I'll give you some references, but they're journal publications and ASME standards. They're not the easiest things to read, but I'll give you them to you anyway.
Okay.
Any other questions? Okie doke. Have a good weekend. All right. Sorry?
At the end.
No, I want to take.
Oh, okay.
And to talk to them. I don't want to talk to them. I want to see the attendance.
Oh,
Is it mute?
yeah, you can just
Right.
on the mute, yeah.
Yeah, mute's
You
on.
use the
See the mute.
mouse, yeah.
Oh, you have to use the mouse.